Hello, good people. We're at Chapter 10, Hypothesis Testing. We're just going to talk about two sample designs today, in this particular file. We're going to talk about independent versus paired, how to do a t-test to see differences between the two. We'll talk about confidence intervals and effect sizes and statistical power in the next video on Chapter 10. So we're going to split it up. So this is going to be the first part of Chapter 10. Another video is going to come for the second part of Chapter 10. Alright, so review Chapter 9 was basically one sample test. And so what does that mean? That means you only calculate one sample, and then you got to compare it to something. So what does that mean? You got to compare it to something that's out there. And so somebody has to give you another comparison. You need some sort of control group to compare against. And so Chapter 9 was the most basic form of a t-test at one sample. So you do some research, talking about the Doritos again. Took a sample of a whole bunch of 8 bags or however many bags of Doritos, and then you compare it to what the claim was, a known claim population parameter. Chapter 10 says, all right, we're done with that. We're just going to take our own samples and see what happens. So Chapter 10 is that you take your own 2 samples and you compare them to each other. So let's talk about how you design an experiment. So the logic is that you start with 2 equivalent groups, 2 equivalent samples. Treat them exactly alike except for one thing, whatever it is you're treating them, whatever the treatment, whatever the hypothesis really is. And then you measure both groups. You attribute any statistically significant difference between the two due to this treatment X. So that's the logic. That's the unicorn of an experiment. This is how we're supposed to happen, but as you can see, again, there's a lot of error involved with this potential problems, or some of these potential issues associated with some bigger error. So let me give you an example. So let's go back to Alzheimer's research. So say you find that you want to do a drug that's going to help Alzheimer's symptomology. So you're in Indianapolis. You're gonna have to give the drug to these individuals with Alzheimer's. So what are you gonna do? You're gonna measure people in Indianapolis with Alzheimer's. Let's say you've got 50 people with Alzheimer's. You split them into 2 different groups, 2 equivalent groups. So you should make sure that they're as equivalent as possible. So how do you make them equivalent as possible? Typically, it's randomization. It's probably the easiest, quickest way to do that. So you randomly select people into 1 or 2 conditions. The conditions are you give one of them a drug and one of them a placebo. So what happens is you treat them exactly alike except for the one thing, the placebo or the drug. That's treatment, yes, no. Measure both groups after, a time period. Let's say you give them a month or a week or whatever. And then you attribute any statistically significant difference in whatever it is you're measuring because of the treatment, the yes or no drug. You can imagine 2 equivalent groups kind of tough. Would you rather have 2,000 in each group? Absolutely, but maybe we only got 25 in each group. So treatment is the one value or level of the independent variable. So let's go back to the designing the experiment. If you're going to design an experiment, you're going to say, all right, what's the independent variable? What's a dependent variable? Let's go back in time. So if we're talking about these Alzheimer's drug, then you've got your independent variable is the drug, yes or no. You think it's going to have an effect on symptomology. Say symptomology is your dependent variable here. The group that gets the drug is called the experimental group. The group that gets the placebo is the control group. So that's sort of the nomenclature I want you to be familiar with moving on from experiments and that sort of thing. All right, so let's talk about the logic of a 2-sample test. So the logic is the same for null hypothesis testing. It's just you got your own 2 samples as opposed to just 1. So number 1, start by assuming the null is correct. So you start assuming that the group that has got the treatment, let's say treatment is A, no treatment, not the drug versus no drug, we start assuming that they're equal. So your null is that they're equal. You decide it's a 1 or 2 tail test. We talked about this a little bit before, but you got to figure out if you got a 1 or 2 tail test. Briefly, what does that mean? That means if you don't know what you're doing, and you don't know which direction these 2 groups might go, either this one's greater or less than, or this one's greater than or less than, you need a 2-tail test. What you end up doing is you end up splitting that 0.5 and into the two tails. So in one tail you got 0.025, and in one tail you got 0.025. So it actually makes it more difficult to find statistical significance, because now you got to split that 0.05 into two tails. If you do know what you're doing, meaning you have a directional hypothesis, you say that the drug group is going to have less symptoms than the group that does not get the drug. Then you have a one-tailed test, and you get to put all of your 0.05 into one of the tails. And so you'd want all of your 0.05 to be in one of the tails on the lower end, so then you can figure out if this ends up being less than this. So that's how you decide if a one or two tail test. When it comes time to do a quiz or a question or whatever, it should be somewhat obvious from the setup. If there's a directional hypothesis, the hypothesis is that it's going to be lower, the hypothesis is that it's going to be less than, then you'd say it's a one-tailed test. If it doesn't give you any sort of directional hypothesis, the alternative hypothesis doesn't give you a direction, then you're going to assume it's a two-tailed test. Set the alpha level. This is sort of your call, but not really if you want to publish anything in any sort of journal. Typically it's 0.05. So that's the alpha levels. You got a p less than 0.05. Take samples, use a t-test. You compare the critical t-test value from the experiment with the critical t-value that you look up in the appendix. So again, in chapter 9, you calculate a t obtained. You find out if it's more extreme than your critical t-values. If your t obtained is greater, then you reject the null. It means you're in the designated rejection region. If your t critical obtained is less than what your critical values are. If your t obtained is less than your critical values, that means it's not as extreme, it's toward the middle, then you retain the null, and so you say that there is no statistical significant difference. Always want to calculate an effect size, because that separates you from other people who don't know what they're doing. And then you've got to write a conclusion. So you realize in these worksheets and on the quiz, I'm going to ask you to write more, and it's going to be even more for the final quiz. And the final exam is going to be a lot of writing. So it's going to be, you need to focus on how to verbally explain what's going on here. All right, so let's talk about paired versus independent sample designs. This is the biggest thing you got to figure out right away. Why do you need to know this? Because at the very bottom of this bullet point, you need to know difference because you use different equations to find the t-values. So if you're going to do this work, you're going to try to figure out if you've got a significant t-value, whatever, you're going to need to know if you're a paired versus independent because you use different equations to do so. So if you use the wrong equation, you're going to get a wrong number and bad things are going to happen. So you're going to have a bad time. So let's figure out the paired. We need to figure out how to identify paired versus non. So a paired sample is a design in which scores from each group are logically matched. It doesn't mean they're all matched. It means that there is a particular score in one group that is logically matched to another particular score in the other group. So there's three different types, common types of paired sample designs. So let's talk about this first one, this natural. The natural one is if you got the father-son. If you remember, we're talking about correlations, father and son height, that kind of thing. They're naturally paired. Why are they naturally paired? Well, because actually they share half their DNA, so they're naturally paired that way. So if you've got family members, another one is like couples research, like if you do dyad research when you're talking about couples. This is sort of how it works with that. So if you've got like, if you're in some sort of relationship, and that those two individual peoples are in a relationship, then we would say that's a natural pairing. You can do matched. So what does this mean? When you purposely put people into groups based off of some sort of piece of information, then you say we're forcing a match upon that. So what's going on here? So let's look at this IQ and hypnosis. I think there was an example talked about in your textbook about this idea that they thought that IQ had a relationship with hypnosis. I'm just going to go on a limb and say that maybe people with lower IQ tend to be hypnotized more versus not. So what did they want to do? They wanted to make sure that they had equal numbers of high and low IQ numbers in each group, so they matched a high IQ with another high IQ, and then they separated them into groups, and so they matched them to begin with. So that is a paired sample design. it's going to be very, very obvious when it comes time to the design setup. They have to say that specifically and explicitly, and so you'll know that you're dealing with a paired sample design. A split litter, what does this mean? This is when we're talking about mice and rats. So typically a lot of research is done on mice, and so what that means is that you've got mice from the same litter. So if you've got 10 mice, you probably put 5, you got 10 mice from the same litter, you put 5 into one group and 5 in the other. They're matched because they share DNA. It's very kind of natural kind of stuff. And yoked is that you purposely, force them to be together. So let's just say if you're talking about, like, I don't know, roommate research. So we were going to do some research on your roommate. You and your roommate are paired, not necessarily naturally. I didn't force you to live together beforehand. You just were naturally sort of yoked together. So that's another sort of matched. And probably the most common paired design is a repeated measure design. So the repeated measure design is basically it's the same person that has 2 different bits of information that go into the average. So what does that mean? So if, I think there's an example in your worksheet or somewhere else that was talking about this idea of any sort of pre-post test. So let's say you're going to go on a week-long training seminar on how to be a better manager. I test your managerial skills before you go. I get your average, and then I test you again after the week-long managerial retreat, improvement, whatever, workshop. And then I test your managerial skills then. It's a paired design because your score beforehand shares the same amount of error as your score after because it's you. It's the same person. Repeated measures means you repeat the same measure on the same person. So it really comes down to error of why we need to deal with this as a different kind of metric when it comes to the equations. So repeated measure is probably the most common form of paired design. An independent sample design are designs with samples whose dependent variable scores cannot logically be paired. So if there's no reason why, first of all, if you're using the same person over and over again, you know you're dealing with a paired. But if you're dealing with different people, some of them got the drug, some of them didn't. Some of them were randomly assigned to the group, some of them weren't. So let's go back to this managerial example. So let's just say we want to find out if this management workshop was effective. Well, what we could do is we take 25 people who go through the workshop, and then we can take 25 people who do not go through the workshop, and at the end we can measure their managerial skills. We would hopefully assume that they all had no managerial skills to begin with, and then we would like to see a big difference at the end. There would be those 25 people that went before, the 25 people who didn't get to go and the 25 people who did get to go, there's no reason why a single person in that 25 is linked to another single person in that other 25. That would be just, we randomly assign 25 people to that group versus not. So those things are independent. So if you got more questions about that, send me an email. It's because you need to understand this before you do any of these equations. All right, so here's the independent sample t-test. What do you want to see here? We got an average of one group here, the difference between that and the other average, and we got the standard error, the difference. And so we got the standard deviation. This is the error term for each of the 2 groups. We subtract them from each other. I will give you this, or I will give you the means in order to calculate this very much more easily than calculating the entire standard deviation. So for your homework, go ahead and look it up in the back of the book. I'll give you a roadmap to it on a quiz or a worksheet, whatever. I'll also give you the degrees of freedom when you need them. I'm also going to tell you how to calculate degrees of freedom. In the worksheet, I told you about an independent samples that you take n, the n of sample 1, which would be n of sub 1, add n sub 2, the number of people in group sub 2 in the second group, and you subtract 2. That's how you end up getting degrees of freedom. So I'll either show you how to do that, or you know how to do it right here. So this is what an example written conclusion would look like from an independent sample t-test. So this is probably something you just want to sort of almost, I don't want to say memorize, but like this is the format that I'm looking for when it comes time for you to verbally explain what's going on in a t-test, in a two-sample t-test. So let's just read this together. The experiment shows that participants exert less effort when working with a group rather than working alone. Participants exerted significantly less effort pulling a rope when they thought that they were part of a group, X bar of 39, than they did when they thought that they were alone, X bar 57. So this, let me give you a background on what this experiment is. So this is a classic experiment where I ask, imagine yourself putting into a room of just like an experimental room in the basement of the psych department. And so you just walk in this room and there's nothing in this room except 2 holes in the wall and a rope going through the middle. And so basically I say, all right, go into this room, and what I want you to do is I want you to pull as hard as you can on this rope in a particular direction. And that's it. So I say, go in the room, pull the rope, whatever. Another group of people, a different group of people, so let's say I had 50 students come in and do that. So I said, here, go in this room, pull on this rope as hard as you can. We're done. Then I tell a different 50 students to come into the same room, and I say, I want you to pull the rope, but I want you to know that that rope is going through 4 walls, and there are 4 other people, or there's 3 other individuals pulling on this rope at the same time. So we're all going to be measuring how much everybody can pull together. So you're part of a group. And so this experiment showed that participants exerted significantly less effort when pulling a rope when they thought that they were part of a group. All right, so if they're part of a group, that second scenario that I mentioned here, they averaged 39.71, I don't know what this means, kilograms of pressure or whatever. But if they thought they were alone, they pulled 57.33. So in essence, they're pulling harder if they think they're alone than if they're with a group. So if this scenario was, I've got an average of 39.7 for people who were in a group, and I've got an average of 57.33 for who thought they were alone, what do? I do a t-test. We follow the same t-test, the same process that we did from last chapter. You identify the t, you look at the t obtained, so you calculate T obtained, you look at the T critical. If it's reject, you reject. If it's not in the rejection region, then you retain. So for this would be an example of it's less than 0.2. So this is telling me that this is less than 0.5, so we're rejecting. So if we were going to reject this, we would say this whole thing. And the experiment shows that participants exert less effort, so I need to know direction. Less effort when working in a group than when working alone. I also want to know the averages. So in alone, I was told down here it's 57, and if you're talking about when you're in a group, it's 39, and I was told the p-value. So I want to know how significant these 2 differences are. Alright, so for a paired sample t-test, the only difference here is that we've got x bar minus y bar, and the standard of the difference is sort of pooled because they share a little bit of the same error. So again, I'll give you this value, or I'll be able to show you how to calculate this relatively straightforwardly. And the degrees of freedom are actually slightly different. Again, I'll give you them, or I'll show you how to get to them. But in essence, the degrees of freedom are the number of pairs you have minus 1. If you have pairs, so say you've got 25 people in one group, you've got 25 people in the other group, they're paired, that means you've got 25 pairs, which means you would have 24 degrees of freedom. So this is an example of a written conclusion for a paired significant t-test. So we read it together. The experiment shows that the participants displayed more positive attitudes about race after a week-long community day camp. Participants displayed significantly more positive attitudes after completion of the camp than they did prior to the camp. P is less than 0.03. I don't really list P is less than 0.3. I think I pirated this from somewhere else. This is less than 0.5. It's also less than 0.1. So just stick to 0.1, 0.5, and 0.01. So this is obviously very, very specific. It tells me exactly what the p-value is here. But it's less than 0.1 is what this is saying. It's not less than 0.01 because it's greater than 0.1, so it's got to be less than 0.1. So what's going on here? The background for this is that we've got students going to a week-long community day camp focused about race attitudes. So imagine having, I don't know how many kids these were, so let's say there's 50 kids that went to this camp. So we got 50 kids, so prior to their attitudes, so let's see, participants displayed significantly more positive attitudes. So we're measuring positive attitudes. So before the camp, we asked them what's their positive attitudes about race prior to, with an average of 28.3, whatever. And then after the fact, we measured their positive attitudes, and they got an average of 34.142. So I want to know if this is a statistically significant difference. I gave it a t-test. I followed the same process. Obviously, this is telling me that it is. So basically, I'm saying the experiment shows that participants display more positive attitudes after. So you're basically telling me after the day camp, things went up. You told me precisely what these were. You gave me both the averages, and you told me what the significance level was. And you use the word significantly more. Significant. This is what I need you to make sure you can put that word significant